So we had done, this is the 5B stuff, the kinetic energy stuff, whoops. And we just came down to this, which you probably remember from physical science. That's sort of a joke. I know nobody remembers anything from physical science, but I like to joke. So, and we did, there were, and I apologize, there were 2 slides that were out of order. I don't know how they got that way, but they were out of order. So doing that entire derivation before we talked about the fact that Ke is equal to 1/2 mv squared is awful. But, you know, Ke equals 1/2 mv squared. So if I give you the mass, or I give you the velocity, or I give you the kinetic energy, you can find any one of those other things. So it's just 3-part algebra. Yeah, you're going to get a couple equations in short order that you're going to want to put on your note card. Okay. So we have that. And then we went into this whole thing. And this was the derivation where we went from F equals ma and W equals F delta x, plugged in the A delta x for work, used one of our kinematics equations, and we end up coming up with this. The work that's done is equal to 1/2 mv final velocity squared minus 1/2 mv initial velocity squared. Well, guess what this is equal to? Think back to here. If we say initial, this is suddenly the initial kinetic energy. The kinetic energy something has when it's starting out. So this is Ke initial. What's this? Ke final. This is really, really useful when something is changing velocities. When something strikes another object and slows down, bounces off of something else. So, okay, so we talked about kinetic energy. What is energy? These are totally out of order, I apologize. We talked about the fact that velocity is more critical. We looked at the NASA video, looking at the fact that, you know, a 2-pound piece of foam can blast a hole through the wing of a space shuttle. Now, we want to look at that derivation. Okay, so we get to here. Work done is equal to the final velocity, or the final kinetic energy minus the initial kinetic energy. Well, anytime we have, you know, something final minus something initial, what do we tend to call that?
Delta.
Yeah, that's just the change in, which gets us to the following. It gets us to the fact that the net work is equal to the change in an object's kinetic energy. This is called the work kinetic energy theorem. And I am not enough of a mathematician to give you a formal definition for theorem, but it's something that's true in math. If you want more detail, go ask a math teacher. So it's this true mathematical relationship here. And we can use this to solve problems. When we sort of add it, that shouldn't be a bullet point. There was a return there that shouldn't have been there. We can use the combination of net work and knowing that net work equals net force times distance to solve problems. So basically we have 2 more pieces of information. Because now what you know is that, well, net work equals 1/2 mvf squared minus 1/2 mvi squared. And net work also equals force times distance. You see what's coming. Force times distance is equal to 1/2 mvf squared minus 1/2 mvi squared. It looks terrible, but it's really not. I swear to you. It looks much worse than it is. Okay, so let's practice. Page 175. Okay, so we have a sled, and we can approximate the sled with a block. We're told that the sled has a mass of 10 kilograms. This one seems fairly terrible, but it's not. We're told that on this frozen pond, there's a 10 kilogram sled. Somebody kicks it, and that gives it an initial velocity of 2.2 meters per second. I'll just go ahead and photograph this. And what we want to know is how far does the sled move if the coefficient of kinetic friction between the sled and the ice is 0.10. So we've got the mass, we have the initial velocity of 2.2 meters per second squared. We know what the final velocity is. What are we interested in? The point when the sled stops. So final velocity is 0. And we have mu k of 0.10. So we've got a lot of pieces here. We'll take this part to the next page. Here are the two things we know. We know that the net work on the sled is the net force times d. And I'm going to make a note here. I'm going to put a sort of an asterisk that this is the force Gesundheit on the axis of the work. And so we want to use the relationship between the force and the work, okay? So it's sort of an informal note. You know, your book just says force times cosine, and remember we saw a case on the 5th quiz where that wasn't quite the truth. So I'm just sort of putting that note in there to like, hey, look at this and look at which, you know, what's that angle between the force and the work. Okay, so we know this. The other thing we know is that that net work is equal to the change in kinetic energy, which means 1/2 mvf squared minus 1/2 mvi squared. Okay, we have two pieces of information here. What is the force that's acting to stop the sled? Friction. Yeah. So the force we're interested in here is actually the force of friction. Okay. And once the sled is moving, there is no other force acting on it on the x-axis, on the plane of the motion. So really, it's also the net force, you know, which is convenient for us, because the y forces are balanced. Once you stop having your foot in contact with it, you're not acting on it anymore. You're no longer exerting a force. Okay. Okay. So we can get to here. What are we looking for in terms, we're looking for distance. So that means that and let's simplify things as much as possible right off. What's our final velocity?
0.
0. So that whole thing goes away. So we now have this net force times distance equal to the negative of 1/2 mvi squared. And we have vi squared, we have mass. Again, solving for distance. Okay, do we have any problems yet? Oh, we don't have the friction. Oh, do we have a means to find friction? Yeah. And this is one of the, I won't say it's terrible because it's certainly not anything like the 4D problems, but we do have to then say, well, if force of gravity here is 10 kilograms times negative 9.81 meters per second squared. And that's going to equal normal force because Fg plus Fn equals 0. So negative Fg equals Fn. And we're given the coefficient. Can we find the force of kinetic friction? Yeah. Let's shrink this. So mu k equals Fk over Fn. Mu k Fn equals Fk. Mu k times negative mass gravity equals Fk. And if we look at the, again, this is just like proving what we already know. If we look at a quick sum of forces on the x-axis, it's equal to mass acceleration, which we're not terribly worried about, but it's equal to Fk. Oh, yeah. There is no other force on the x-axis. So whatever acceleration is occurring is equal to Fk. So since this is Fnet, Fnet equals Fk. Okay. Ha. Okay, get it? The distance that the sled travels is equal to 1/2 its mass times its initial velocity squared, all divided by mu k times negative mass gravity. Now there's one thing that we've kind of left out here. And that's the fact that the distance it travels, the direction it travels, what's the angle between the direction it's traveling and the direction that the force is acting on it? Let's think about a force diagram for this. So it's traveling this way. Which direction is the frictional force acting? That away. So this is actually Fnet, and this is where we would use cosine theta. And what's theta? 180. It's in opposition. All the cosine of 180 is -1. So this is just telling you that the work that's being done is being done against the motion of travel. So cosine 180. Let's take this to the next page. And we'll go ahead and put in our values. Okay, so you can certainly take this to the bottom, which is what I've done here. Okay, so now let's get a raw answer. Okay, what do you have for a raw answer? Yeah, 2.466870054, etc. And we get a positive number. You've got 3 negative signs in there. You've got this, you've got this, and then this gives you a -1. It ends up, because, 4, because you've got this one. So it ends up as a positive number. The distance it's traveling is positive. The work done on it, if we were to solve for work, is negative, because it's slowing it down. They're not hard. They're certainly, like I said, nothing like what you saw in Chapter 4. I'm going to assign 1 through 5 on page 176. So page 176, numbers 1 through 5. You have the rest of the time to work. And I think tomorrow we'll work the first half, and then second half I have a 5B and 5C FIB quiz. 5B is so easy, it's kind of a, it's a toss-off. But 5C is a little bit more work. So that's where we'll be tomorrow. And you can just work now.